Good afternoon, everybody. I would like to welcome you to what promises to be a fascinating event with the IceCube team in the USA, South Pole, and France, as well with our alumni and friends from around the world. I am Daniela Bortoletto. I am the head of particle physics in Oxford. My physics research focuses on the study of the Higgs boson with the Large Hadron Collider, but I truly find neutrino fascinating and mysterious. While the LHC result indicates that the Higgs field gives masses to quarks and charged leptons through the Yukawa coupling interaction, neutrino might be special. Neutrino aren't massless, but they're just incredibly light, 1 million times lighter than the next lightest particle, the electron. Trillions of neutrino pass harmless through your body each second, and in fact, rarely interact with any matter at all. This year sees the 10th anniversary of the IceCube Neutrino Observatory. So the detection of the Glasgow resonance back in March seemed like a fitting breakthrough, which we should celebrate today. We are really excited to share some of this research with you this evening. We have a few speakers lined up for you today, and so now we should start. And please use the Q&A boxes to ask questions throughout the event. We will select a few and we reply at the end. So let me introduce a few of the people that we have here, okay? They are coming from all over the places, actually. We have Jim Madsen, the Executive Director of the Wisconsin IceCube Particle Astrophysics Center at University of Madison in the US. We have Gwenhaël de Wasseige, who is joining us from France. And at the South Pole, we have Josh and Martin, who are the current winterovers. But first of all, it's my pleasure to introduce my colleague, Professor Subi Sarkar, who started his career at the Indian Institute of Technology in Kharagpur back in the 70s and has developed an incredible career working in Oxford physics. And he also worked at the Rutherford Appleton Laboratory, CERN, among others. He has also been the head of particle physics theory group and the Niels Bohr professor at the University of Copenhagen, as well as adjunct professor at the Raman Institute in Bangalore. His interests are focused on the interface of fundamental physics and astrophysics and cosmology. And since 2004, he has been a member of the IceCube Neutrino Observation Collaboration. So let's go to Subir now. Welcome, Subir.
Hello. Thanks very much, Daniela. Sorry for joining a bit late. My other talk overran. It was actually in Chile. This is how it goes. I think what I should say is that normally people expect experiments to be done by obviously experimentalists who do the hard lifting. In this particular case, my involvement in IceCube is as a theorist, because IceCube is a very unusual collaboration. It was an experiment that was very much sticking one's neck out and going for a outcome which was by no means guaranteed, and there were many setbacks on the way. And in that respect, it is quite different from the kind of experiments that are done at big laboratory accelerators such as the Large Hadron Collider, where there is some kind of a roadmap for how you go forward. Whereas astroparticle physics, which is what we are doing at IceCube, is partly like astronomy. The discoveries are serendipitous. They're not predicted or forecast or guaranteed in any way. So I would say that my role in IceCube is therefore to provide theoretical inputs and firm up the physics targets that we go for. And in that respect, I've been very fortunate that at Oxford, we have the support of a wide range of people in many relevant disciplines, in particular in particle physics and in astrophysics. And therefore, we are able to make, I think, contributions to IceCube, which have been of some use. But let me now move to introducing my colleague, Jim Madsen from Wisconsin, who is a proper experimentalist and has worked on IceCube at the nuts and bolts level. He has probably been to the pole more often than I've had hot breakfast. He is the executive director of the Wisconsin IceCube Particle Astrophysics Center. And he in particular has a strong interest in outreach and education with the work that we do, and has done a huge range of activity in that regard. A few that I can mention is engaging with school teachers, in fact, even arranging for them to visit the pole. Today, our visit is only virtual, but we are delighted that Jim has arranged for us to talk real time and live with our two winter rovers who are right now at the pole in darkness. And so without further ado, let me now ask Jim to present something about IceCube, give us the overall briefing of the project. And Jim will be joined with Gwenhaël, who is one of our young stars in IceCube. It is really the young people in the collaboration, not to sort of say something very obvious, who are our future. They represent for us the new ideas, the new directions in which our collaboration, we hope, will evolve. Over to you, Jim.
Yeah, thank you very much. It's a real pleasure to be here. Let me just start to share my screen and make sure that's all working. And I'm going to go here and do.
Yes, that looks fine.
Good. And then make sure this goes. Okay, we're working okay. So I'm going to do the first half of the presentation and then turn it over to Gwen. And so as Super said, we're super excited to be here, and we'll just get going. So this is a real color picture, not been touched up, from the South Pole, and the building you see there is the IceCube Laboratory. Okay, this is one of my favorite photos in science, and it's actually been made into a video. This is the Hubble Deep Field image, and it was taken by focusing on a previously thought empty spot in the sky and collecting data for almost 2 weeks. What's amazing about this is each one of these smudges you see there is actually a galaxy. It takes light roughly about 100,000 years to go across each one of those spots, and then the distance from galaxy to galaxy is about 1,000,000 light years. And so this is an incredibly tiny spot in the sky. It takes about 11 million of these swatches to cover the universe. And so contrary to what you might think, it's actually, the issue is not always, is there something out there, but is the thing that you're seeing what's actually doing what you're measuring. And so what we know is that we are getting incredibly high energy particles from outer space. Cosmic rays themselves were discovered a little over 100 years ago, but in 1960, this phenomenally high energy particle was detected. Really 1,000,000 times more energy than the highest energy particles we can produce at laboratories. And so still, there's maybe 1 or 2 sites, thanks to IceCube, that we know where these particles are being produced, but we don't know how they get such high energies. And in order to solve that mystery, we have to look in new ways. So let me just tell you what I know about astronomy. And that's basically that stuff is too far away for us to go visit directly, and the conditions are too extreme for us to reproduce in the laboratory. So what we have to do is devise instruments in order to take in whatever those objects can produce. So the first people did astronomy just with their eyes, and now we have these detectors. What we'd like to know is these cosmic messengers, where are they coming from, how much energy they had. Sometimes we'll see when we saw it was important, and then what type of messenger. And so I really like this picture. This is one object in the sky viewed from multiple different wavelengths, and kind of to give you an idea of what you see depends on how you look. There's also a picture of your hand, right? Whether you do that with visible light or whether you shine it with X-rays. So if you had something wrong with your hand and it's not on the surface, taking multiple pictures with an ordinary camera would not divulge where that cracked bone is, for example. But we see that right away with an X-ray, in the same way as when we look out in space, right? We get new information that complements other ways of knowing. So that's the whole idea about looking for neutrinos from space. So just to give you a quick background, right? The neutrinos come in three types, which physicists call flavors. There's an electron neutrino, a muon neutrino, and a tau neutrino. And this little cartoon here is supposed to represent that these neutrinos mysteriously, right, exist as all three types at once. When they're created, they're one type. When they're detected, they're one type. But in between, they oscillate from one, in some sense, exist at all three types at once. And as was mentioned, you have this phenomenal number. Neutrinos behind photons are probably the most abundant particle in the universe. So 65 million through your thumbnail, so that means, you know, trillions per second through your body. So how did we get to this spot? Real quickly, I'm going to just give you some whirlwind tour here, and it was, you know, for me, not, it doesn't seem like such a long time ago, but you know, the end of the 19th century, right, when X-rays and radioactivity were discovered, when and that's really what drives science, right? Is new information. And when we started to investigate that radioactivity, if all that was happening was a single particle coming out, which is what had been detected at that point, then we would expect that all those particles coming out would have one energy. It's basically, there's two particles, two conservation laws, so there's only one answer. Okay, but when they actually did the measurements, instead of seeing one energy, they saw this whole distribution of energies for the particles that were coming out, and none of them were at the expected energy. And so that causes a lot of consternation, because conservation energy, conservation momentum are cornerstones of physics. So 20 years after that, right, Wolfgang Pauli, this famous quote, he says, maybe there's a third particle that we just don't detect. And he says, I've done a terrible thing. I postulated a particle that cannot be detected. But again, once you start thinking about it, people say, well, what were that properties of that particle have to be? How could we find it? And what we know is these neutrinos should be produced whenever particles are changing identities. So that could happen in radioactive decay, it could happen in fission and fusion. And so we could look at atomic bombs. There were issues about that, looking for neutrinos from there. So, but finally, Cohen and Reines got the idea of putting a detector near a nuclear reactor, and had the advantage that they could turn the reactor on and off because the signals were very low. You wanted to make sure you weren't missing just some background. Okay. So then once these neutrinos were established as real, then the next question is, can we see neutrinos from outer space? And so, you know, 1960, it gets proposed that we could put a detector in water, right? And then use those detectors to determine the direction of these neutrino interactions. Okay. And so the issue again with the neutrinos is they have many powerful properties. They're neutral, so they don't get deflected by magnetic fields. They're essentially unabsorbed, so they travel intact from their creation source. They track nuclear processes. Potentially will reveal the sources of cosmic rays and probe new physics. But the downside to all those is that they're very difficult to detect and would need the largest science instrument ever built. So I'm going to just go quickly through this, right? The idea, as Markov and Pentokova said, is you put light sensors in a transparent medium. The neutrinos themselves are invisible, but when they interact, they create charged particles. Those charged particles produce light in this transparent medium, and you have a grid of light sensors that pick them up. And from that timing, you can determine the direction, and the total amount of light is the energy. So what we did is not work in water, but we actually worked in ice, another transparent medium, at the South Pole. And so over the course of about 7 seasons, we drilled 86 holes in the ice down 2,450 meters and put in 60 light sensors in each hole. So roughly a cubic kilometer of ice that's been instrumented. And here's some pictures of what that was like during construction. And just to give you an idea of how big an operation that was, here's what that drill site looks like. And so, as I said, the neutrinos themselves are invisible, but when they interact, they'll produce charged particles, and then those charged particles then will produce light that we can pick up. Okay, and so I already talked about what the power is of these neutrinos, and so we won't go into that. Neutrinos are just one messenger that's coming, so where we're making progress is by looking at multiple measures and messengers. Gwen's going to talk about that. This is a quick animation that shows how this would work in principle, right? The white is supposed to represent the neutrinos, and the kind of purplish ones are like gamma rays or other high energy light. These neutrinos come in, right, and now they're going to encounter some water molecules eventually here. You'll see that, and then some unlucky neutrino encounters a proton or a neutron. That produces a charged particle called a muon that's going through the ice, giving off light. Then we have our light sensors there that are going to pick that up, and there we go. And so, you know, I really like this quote from Art, right? You know, the idea of art, and then I think also in science, is not just to produce what you can already see, but to make things you can't see visible, right? So this takes a large group. In addition to Subir, there's about over 325, 350 scientists involved, and almost that many support people that help build and maintain the detector. And here's an example of our recent collaboration meetings, which for everyone has been online. So with that, I'm going to turn it over to Gwen.
Thanks a lot, Jim. Good evening, everyone. I think you should be able to see me in a few seconds. I'll start this way. So good evening, everyone. It's really a pleasure for me to be with you today to talk about the science we can do with IceCube. And preparing for the event, I was trying to figure out an image to show you, to share with you, to give you a direct idea of what IceCube presents to me as a young researcher. And I came up with the idea of a Swiss knife, because IceCube turns out to be such useful tool, to study many fields in science. So obviously we have astrophysics, and I'm going to go in details a bit more on this topic. But IceCube can also provide very useful information on the neutrino itself, on the intrinsic properties of the neutrino, such as, for example, how neutrino would oscillate. You might know that there is a model that describes the elementary particles and their interaction between themselves. And this model is called standard model of particle physics. And clearly one of the big game in physics today is to try to see if this model really describes well nature, or if there are some slight deviation from this model. And IceCube can help us trying to find this small deviation. We can also search for dark matter, for example, dark matter annihilation in the center of the sun or in the center of our galaxy. And we can also study fundamental symmetries and Earth science. So who would have guessed that a neutrino telescope can actually turn out to be very useful for glaciology? So as I said, I'm going to go through some breakthrough made by IceCube. And obviously, as I'm myself more involved into astrophysics, I'm biased, and so most of them will be related to astrophysics. So let's go on with the first one, the first breakthrough that was announced by IceCube in 2013. And you see that it actually got the label Breakthrough of the Year from Physics World. It was for the discovery of a high-energy astrophysical neutrino flux. So you see the plot on the left part of the slides represent the astrophysical and atmospheric neutrino spectrum. So, like in simple terms, is the number of neutrinos you would have as function of the energy. And so you see the different components we are going to expect. For example, solar neutrinos in pink, and then we have supernova neutrinos in red, and then the atmospheric neutrinos, which are neutrinos produced in our atmosphere by high-energy cosmic rays accelerated somewhere in the universe coming to hit our atmosphere. And then IceCube came and discovered a high-energy astrophysical neutrino flux you see at very high energy in blue. So it made, at that time, it made the cover of Science, so it really shows you that it was a big thing. And just to give you a feeling of how this, the event selection was on, how we managed to extract these very special events among the huge data sets recorded by IceCube, I put a sketch here where you see that we have our DOMs, all our sensors in IceCube, and we built an imaginary veto layer around it. And we knew that our special neutrinos would only leave a signal inside of the detector, deep inside of the detector, and nothing around the veto. So searching for this specific signature, and also for event that produces a lot of light, because we were expecting very high energy to be left in the detector when the neutrino interacts with the ice, we managed to extract these very special neutrinos coming from somewhere in the universe. When you know that you have high energy neutrinos produced somewhere in the universe, you want to know where they're coming from, right? And one of the ways to do that nowadays, and it's actually a quite young field, is to use multi-messenger astronomy. So multi-messenger astronomy is the idea of not looking at the sky using only one messenger, for example, using only light, but by combining the information from different messengers. So electromagnetic waves, light, gravitational waves, neutrinos, and cosmic rays. And even though it's a rather young field of study, as I said, it already had several major achievements. For example, the supernova of 1987, which was seen through both electromagnetic waves and neutrinos. We also had the binary neutron star merger that you might have heard of, GW170817, which was seen through electromagnetic waves, so light, and gravitational waves. So we did search for neutrinos from this specific event, and actually for every single event that have been detected so far by the LIGO and Virgo interferometers, you know, these new kind of detectors that are sensitive to gravitational waves. But up to today, we haven't found yet an event that is shining through gravitational wave and neutrinos. And then finally, in 2018, came a flaring blazar called TXS 0506-056, which was seen both through electromagnetic wave and high energy neutrinos. And because these two messengers were detected from T-specific source, it automatically made it a cosmic ray source as well. So this is the very first source that has been seen through these two messengers. So let's look a bit closer at this event. So as I said, when you know you have a high energy astrophysical flux out there, you want to take all the chances possible to try to characterize it and to know from where it is coming from, where in the universe it is coming from. So one of the techniques that is used by IceCube is to constantly monitoring what is happening in the detector, what is happening in the ice. And then when something big is happening, when one of the special events is happening, we just send out the information to our colleagues, to our partners, which are searching for electromagnetic waves or gravitational waves. And we say, oh, look, we've seen something interesting right now coming from T-specific direction in the sky. Can you point your satellite or your ground-based experiment to look into this direction to see if you also see a signal in this direction? And so in September 2017, that's what happened. There was a very bright event in IceCube. We sent out alerts, and it turned out that actually in this very special location, there was a blazar that was in a flaring activity. And so you see here the different partners that have been searching for a signal in this direction. And so it really makes it special because it's the first event we see through electromagnetic waves and neutrinos. And what is even more special about this event is that once we knew there was this interesting source at that specific location in the universe, we went to look at our own data, at our own archives, to see if we didn't see something interesting before in this location, but didn't notice it. And actually, it was the case. So you see here the second major result linked with these specific sources. So what you see here on the vertical axis would be kind of the number of neutrinos you would detect. And on the x-axis, what you're going to see is the time. So from 2009 to 2017. And so at the very right of the plot, you see when there was this very high energy neutrino that started the whole story. And then in 2015, end of 2014, 2015, you see that there is kind of a peak in the orange and the blue curve. So actually, we had already detected many neutrinos coming from this specific source. So from the same source, we have two distinct, very remarkable observations. One of a very high energy neutrino and electromagnetic waves, and one of many neutrinos coming from the same place. So let's move on now to the third major achievement that I'm going to talk about today, which is the first observation of a glacial resonance event. So it has been announced only a few months ago, and it was an event detected in 2016. So this is just to give you an idea of how complex we're dealing with neutrino detection, but because also it was the very first event. So this is a specific neutrino interaction. So Jim told you that neutrinos will interact with proton and neutron in the ice. Actually, in this case, the neutrino is going to interact with an electron. And if the neutrino has a very specific energy, and if the neutrino has a very specific flavor, then the probability for this neutrino to interact with an electron is boosted by a very large amount. And so first, we have more chance to see this interaction, and then it also directly give us an idea, a precise idea about the nature of this neutrino, and hence the nature of the source that has been producing this neutrino. And so clearly this is a major breakthrough, because it's the first time ever that we have seen this interaction predicted in the 60s. So let me move on to the last part of this presentation, which is the future. So clearly, and I hope you will agree with me, we have opened a new window on the universe. We have some breakthrough. We know there are high energy neutrinos produced somewhere in the universe. Now what we have to do is to see which answers this specific window can provide to us. So among the questions that we are going to try to answer in the next decade, what does the neutrino sky look like? And so I put here on the right part of the slide, you see an image of this of or you would see the sky if your eyes could see neutrinos. Which are the sources emitting high energy neutrinos, and what are the properties of these sources? And then finally, can we find signs of new physics? Can we find deviation from the standard model of particle physics in nature? So the solution that the IceCube collaboration put together is actually in several steps. The first step, which is arriving right now, like next year, is called the IceCube upgrade, and it will focus towards lower energies. So we know they're high energy neutrinos, so let's try to see at lower energies what we can learn in this energy range, and how it can help us improving what we already know about the universe. And then in a second step, we're going towards IceCube Gen 2. And here we're talking about an even bigger, an even larger detector. We're talking about 8 times the current volume of IceCube. And in addition, other technologies to detect neutrinos, which is called a radio array, which will allow us to detect even higher energy neutrinos. So that will be all for me, but we will all be very glad to answer all your questions about neutrinos.
Great. Thanks so much, Gwen. I think what we'll do is we'll hold questions until after the presentation from the South Pole. I'm really pleased to be able to introduce our extremely special guests who are almost as far away as they can get and graciously have agreed to come and present. So I'm going to turn this over now to Martin and Josh. I'll just say very briefly, in order to do a project like IceCube, you need a wide range of talents. And one of the talents you need is people that are willing to be isolated for long periods of time. So Josh and Martin arrived around December or so, I believe. They got there a little later. And then the last plane left about mid-February. They won't see a new plane at the South Pole until about October. So we call them winterovers for that reason, for being down there. So Martin and Josh, are you there?
Hi, Jim. We are here. Yes.
Yep. Great. Okay. Let me find your presentation, and then we'll get going there. Okay. Oops, I got the not this one. Sorry, I lost my screen here.
Okay, so maybe while Jim is putting up the presentation, maybe just to introduce ourselves. So I'm Martin Wolf. I'm with IceCube since about 10 years now. And this is actually my second winter at Pole.
Yeah, I'm Josh Veitch-Michaelis. This is my first winter at Pole, and actually my first time collaborating with IceCube. So previously I was working in conservation science, doing hardware kind of things. Yeah, so thank you everyone for joining in. Hopefully we can tell you a bit about what life is like down here. And yeah, you can see in the background we actually have a dome, which we took from downstairs.
All right, are you seeing my screen now, the presentation?
Yes, we do.
Okay, let me get to full screen and then. Okay, are we good?
All right. Yeah, so thanks everyone for joining here. So yeah, many greetings from South Pole. So yeah, Josh, you want to say about the first picture?
Yeah, so this is a picture we took shortly after sunset, so probably around March. And you can see in the bottom left, this is the IceCube Laboratory, so ICL. The buildings on the lower right are the other sort of big experimental facilities here. So we have South Pole Telescope on the left, that's the dish sort of pointing to the left, and BICEP Array and Bicep 3. So these are all radio telescopes. You see the moon's up, and you can actually see Saturn just above the south in the title.
All right, next slide. So the question is always, how do you get to South Pole? So the most convenient way is to actually fly. And so you actually fly to Christchurch, and from there you take military airplanes from Christchurch to McMurdo, which is at the coast. And from there on, you take another flight to South Pole. And so flight time is about, from Christchurch to McMurdo is about 5 hours. And from McMurdo to South Pole is another 3 hours, depending on the airplane. Usually we fly with these very large airplanes from the US Air Force, which you see on the upper right. But actually this year, everything was different because of COVID, and we didn't have these large airplanes. We actually flew with the smaller airplanes, so called Baslers, which you see on the upper left. And the good thing is that you can actually, when you fly with those airplanes, you can actually look outside. They have windows, and then when you basically look through the window, you fly over the Transantarctic Mountains. You have really nice views. And once you arrive at South Pole, then the first thing you do is you take a picture at the geographic South Pole sign. And so you see us here on the lower right picture, me on the right and Josh on the left, taking our hero shot, basically.
Yeah, next slide. Yeah, so in the background of the sign on the previous slide, you saw this elevated station, which is where we are now. We are pretty well elevated. We're at around 9,300 feet, which is around 3,000 meters. The kind of feels like altitude here is anywhere from 10 to 11,000 feet, so we're very high. The station's pretty big. It's around 65,000 square feet. And our population this winter is 39, which is the smallest it's been since the late 90s, but not actually that small compared to normal years. And in order to keep the station running for 8 months or longer without any people coming in, we use a lot of fuel, almost 500,000 gallons. And you can see on the top right picture, this fuel is dragged in on what's called the South Pole Overland Traverse. So a bunch of tractors with these big fuel bladders behind them. And this gets taken from McMurdo on the coast to here, and it takes about a month. Otherwise, you can see a picture of our galley where we eat. The food is very good here. And a typical berthing room. This is my bedroom. So people kind of make the station their own, so they don't go crazy over the 8 months.
Yeah. Next slide. So then inside the station is fairly large, and so we have many different rooms and possibilities to spend our time here. So we have a very big gym, actually. So on the upper left picture, you see kind of us where we kind of play dodgeball, and so we can use the gym for exercises. We can use the gym also for a movie theater, which we so after the last plane in February leaves, then it's very traditional to actually watch all 3 movies of the thing, which is very exciting. And then we have also a library, and so on the lower left you see me reading a book there. What's also nice is we have a sauna. So when we get cold, then we can just go into the sauna and heat up. Actually, this morning I actually went to the sauna as well. So it was quite nice. And yeah, so next slide. You see basically on the top left the station. As I said, it's pretty large. So we have like 2 floors. And then the South Pole point is basically marked with a so-called South Pole marker. And every year, the winterovers actually design those markers. And so we have a shelf in the station where we have basically all the South Pole markers from the last years. And every year on January 1st, the new South Pole marker is introduced, and actually the South Pole sign, the South marker sign is actually moved because the ice actually moves every year by about 10 meters, and so we have to move the South Pole sign. And so this is done every year on January 1st, and on the upper right picture you see kind of how we kind of introduced the new South Pole marker. And on the bottom right picture, you see a picture of our emergency power plant. So we produce energy and heat here via diesel, basically. So we have large generators here. We have actually a large generator kind of downstairs in a separate kind of building. And in case we have problems with that, we can basically also use the emergency power plant. Right, next slide.
Yeah, one of the questions we often get is, what do we eat? And obviously over the winter, we have no way of getting in fresh food that would otherwise go off. So there's actually a greenhouse on station where we grow a lot of salads and other what we call freshies. You can see Martin in the top left is sitting in the lounge, which is a nice place to sit because it's very humid, it's quite warm. South Pole is very, very dry. We're in a desert where the humidity is essentially zero. So being able to sit in a kind of a damp place is actually quite nice. We grow some flowers, which are edible. We grow lots of lettuce, lots of tomatoes, cucumbers, all kinds of things. And we harvest around 1 kilogram a week. So enough that we can have a salad, a kilogram a day almost actually sometimes. So we have salads pretty much daily, which is really quite nice. Yeah, we can go to the next slide.
So then we,
yeah.
Okay, it's about weather. Yeah, usually we get kind of questions about what weather is at South Pole. So usually the answer is it's kind of cold. So we have kind of temperatures between in the summertime minus 20 degrees Celsius and the wintertime down to minus 75 degrees Celsius. And then, of course, we have holidays. So because we spend all year here at South Pole, we also celebrate the holidays. So when we arrive, we usually start with Thanksgiving. And then we have a Christmas coming up in December. And then usually we celebrate the New Year's. And then we have sunset dinner. Then the sun goes down in March. Then we have a nice celebration there. So we kind of decorate the galley nicely, and then we sit all together and have really nice food. The food here in general is really nice. This year we have really nice chefs, which are producing really good food. And then when the sun comes up again, so we have then sunrise dinner. And then usually in November we are leaving them again.
Yeah. Yeah, so as Martin said, the weather varies quite a lot here, from clear skies to whiteout conditions, as you see in the top right. In the summer, when the sun is up, you actually get some quite interesting weather phenomena. So the bottom left, you can see a sun halo. This is formed when ice crystals in the atmosphere, the light from the sun refracts through these ice crystals, and you get these halos with lots of interesting features on them. Obviously, the sunset and twilight, we get very pretty sunsets. And of course, because one day lasts a year here, these sunsets can last weeks. We also, as a kind of a station, we monitor the weather. This is important for lots of different things, mostly for flights when they come in. So we launch weather balloons every day. And this is me launching one. So these carry a payload of various sensors, which transmit wirelessly to a receiving station on the ground. We still launch these weather balloons in the winter because that's really the only way we can measure the atmospheric conditions at the pole. We also launch ozone balloons. So there's another group here from NOAA in the US who are basically monitoring climate, and they monitor the ozone hole over the pole. So we also launch these big ozone sondes.
Okay, go to the next slide. Yeah, so of course, when you're living here, then of course you're not always working. You also have some spare time, and so there's also some fun stuff to do. So for example, we have a climbing gym, and so you see on the top left me climbing there a little bit. And then we have also a kind of a weight room where we have kind of also treadmills and a fun thing. So usually to do like a run to Mordor, where you kind of watch all of the Lord of the Ring movies, and then while you're walking there. So yeah, and then of course you can also do like fun stuff in the snow, like snow angels. Sometimes we also do kind of outreach events. So for example, on the lower left picture, you see us reading books at the ceremony in South Pole marker. We had kind of the request that yeah, we wanted to kind of we wanted to motivate young people to read more books, and so we did kind of a picture with us reading books, and then yeah, we can also of course play chess outside if you like. So yeah, that's quite fun. Okay, next slide. Yeah, we then of course, as you saw in the previous slide, we have this tent basically. This is a Scott tent, it's called, and then we also put those tents, or this tent basically up during the winter sometimes, and then you can basically go inside and kind of experience how it would be to spend the night in a tent basically. So you have a lot of sleeping bags in there, so it's yeah, to keep yourself warm, and you can make nice pictures. So yeah.
Okay.
Next slide.
So the end of summer is quite a special event. We have the last plane leaves. So you can see bottom left, this is the Basler, the type of plane that we flew on. Everyone is very sad usually when they leave, or very happy depending on how their winter went, or how their summer went, sorry. And it's usually a big event. Everyone goes out to the observation deck and watches the last plane take off. And of course, at the end of the summer, you have sunset, which I think is probably the next slide. But you get these amazing colors, around on the horizon, like this.
Yeah, right. So sunset is usually around end of March. You kind of so one thing is here, so sunset and sunrises last for a very long time here at South Pole, because basically you have every sunset you have in the north, basically on every day you basically have them combined in one session here. So the sunset lasts for about 2 weeks, and because the sun sets very slowly, you have a phenomenon that you can see at the South Pole very nicely. It's called the green flash. So when the sun goes below the horizon, then the light of the sun splits into their different colors when you go through the atmosphere. And when you're lucky and the weather is nice, then you kind of see this green flash, which you see on the upper picture here. And this year we were lucky again to see kind of this green flash, so it was quite nice. And yeah, and during sunset time you can get very nice pictures with the IceCube lab and the picture and the sun, and then yeah, so it's really nice colors in the sky.
So after sunset comes twilight, and actually, as Martin said, this stuff lasts a long time. So we only came out of astronomical twilight a couple of weeks ago, I think 2 or 3 weeks ago. So you still have these amazing colors. This is again using IceCube and the various other telescopes at South Pole, now with their red safety lights on so that we can see where we're going in the dark. The moon, of course, does come up. So while it's dark 24 hours a day here, we do get a couple of, a week or two of moon, and it's a full moon. And when the moon's up, it's bright enough that you can walk around without a headlamp on, which is pretty cool. And you can see again an ICL in the bottom picture.
Yeah, and then another thing is, of course, when it's dark outside, is that you have basically all these auroras. So all these southern lights, basically. So when kind of the solar wind interacts with the atmosphere and it excites the nitrogen and oxygen molecules, then you get these really nice lights, and they are kind of dancing in the sky around, and it's really nice to watch them. And they make different shapes. Sometimes they have these curtain shapes, which are really nice. And then, yeah, depending on what kind of molecule gets excited, you get the different colors, like either green or kind of red or purple. And yeah, for me, a lot of this red and purple auroras are usually the really nicest ones, and which I like the most.
Yep.
And yeah, and so here we have basically more auroras. Yeah, so you see basically, so on the top left picture is kind of a view from our observation deck from the station. The light on the left is the IceCube lab, and then the light on the right, kind of the dark sector lab with South Pole telescope. And on the lower left, we have our satellite dome, basically. All our communications is, of course, through satellite. And so this satellite dome usually makes a really nice foreground object when you have the Milky Way in the background and these nice auroras. And yeah, you can also stand next to it and make some nice poses and have the Milky Way in the background. So yeah, so the winter time is really nice to get really nice pictures, and which kind of, yeah, it's a good experience here. And then, of course, you can also then just lie around in the snow next to the IceCube lab and watch the sky, basically. And yeah, it's a really great experience down here. Yeah. Thank you very much. Yeah.
Yeah, thanks very much. We kind of rushed through that, but that gives you more time to ask questions. So feel free to ask whatever you want.
Awesome. Thank you, Martin and Josh. We will go to questions now. I'm Madeline O'Keefe. I'm the communications manager for IceCube and WIPAC. So feel free to ask your questions in the Q&A box, and I'll jump to some right now. Let's start with some for Martin and Josh. Do you have to cope with altitude sickness when you first arrive?
Yes. Well, I mean, we take medication called Diamox. So you take that slightly before you leave to get to pole. And generally you try not to do anything too strenuous for the first week or so, because yeah, it's pretty tough. And even now, like walking up a flight of stairs or tying your shoelaces can get you out of breath. So you kind of get used to it, but it's still pretty tough.
Yeah,
it's actually a lot more difficult to deal with than the cold, I think.
Okay. Well, that was similarly, someone else is wondering, they heard the air is thinner on the pole, so is the station pressurized? Or is the difference?
No, the station is not. Yeah, no, the station is not pressurized. We basically have the same pressure in the station as outside, but yeah, it's about 30% less oxygen that we have here at about 10,000 feet elevation.
Yeah. So what time zone do they use at the South Pole?
Yeah, so we are on New Zealand time zone, because that's because we fly through New Zealand and all the logistics are through New Zealand. Then it makes easier to coordinate everything in New Zealand time. But in principle, you could use any time you want, because at South Pole, yeah, it's arbitrary what time zone you are.
Yeah, I mean, if we're doing work with Madison in the north, then we might be working on kind of Madison time. The detector itself runs on UTC. The US Antarctic program is in Denver, so a lot of people, use Denver time to coordinate meetings with people. But on the station, it's New Zealand.
Gotcha. So how does it feel to watch the Southern Lights, and does it happen often?
So it happens basically every day. Of course, it's random. You can't predict when it happens. But we have kind of a camera outside. You can actually see what the sky always looks. And when we see some auroras out there, then usually go out and then we watch it. And I mean, of course, it's very cold, so you can't stay out there for too long. But usually it's enough to kind of take your camera, take some pictures, and yeah, it's really nice because they're kind of they're dancing in the sky, and they're changing very fast, very quickly, and they make very different shapes. And yeah, it's really a nice natural phenomenon to watch.
Awesome. The pictures are just really wonderful that Martin and Josh take from the South Pole. So I encourage you, and anyone who wants to see more photos, our Instagram, our website has lots of the photos that they send. Martin and Josh send us photos every week. It's really wonderful. So thank you. Let's jump to, we still have some questions about IceCube and neutrinos. So we got Gwen and Gwen's video working. So we'll jump to one of those questions real quick. Let's see. How does the interaction of muons with water and ice compare with each other? Are they different, or how does that work? Oh, Gwen, you're muted.
Sorry, my bad. You can either have my voice or the video. We have to choose. So I'd say that actually the advantages of ice and water are different, but both also have bad stuff for detecting neutrinos and muons. So in ice, for example, you're going to have a lot of scattering, but a very small absorption of light. In water, you're going to have almost no scattering, but a bit more absorption of light. And so I'd say that the two techniques are actually complementary with each other. And I'm sure Subir and Jim would agree with me to say that we are very happy to have detectors both in ice and in water as well.
Exactly. Yeah.
All right, thank you.
I'm busy typing answers into the chat boxes. So let's see how fast I can keep up.
Okay, well, we can hop to a couple more questions for Martin and Josh about South Pole life. There are a couple questions about that thing behind you guys, that detector. Can you talk a little bit about that? I think you mentioned it at the beginning, but that is one of the IceCube DOMs, right?
Yeah, so we have around 5,500 of these in the ice. There are two main parts. There's a bunch of electronics on top, and the bottom half is basically a huge light detector. It's a photomultiply tube, which is a very sensitive type of detector. So it can count individual, can see individual photons. There's a cable that it gets is used to send the signal back up to the ICL on the top. And that's more or less it. It's basically just a big light detector and some readout electronics. There are also some flashlight for calibration purposes. Yeah, it's in a big glass sphere. It's quite heavy. I mean, this is there's a very thick glass kind of pressure sphere around it. Yeah, anything else, Martin?
Yeah, no, I think it's just everything. Yeah, I mean, the idea is to detect signal photons with the photomultiplier, and then to reconstruct the neutrino, or reconstruct the charged particle, and then once you know the direction of this, then you also know the direction of the neutrino.
Probably the most important thing is that it can DOMs can measure the timing of events very accurately, because you know how fast light moves even in ice. In order to reconstruct the track of the charged particle that travels through, you need very accurate and precise timing.
Great, thank you. What are the arrangements for medical assistance, or rather, what kind of medical resources do you have at the South Pole?
So we have a doctor and a PA, a physician's assistant. We have a pretty well-equipped kind of medical wing. So only two medical staff over winter. We also have an emergency response team for medical stuff. So there's fire, medical, logistics, and supply. So we're pretty well equipped for anything, or for most things that could happen. Obviously, if there have been medical evacuations in the past, but that's extremely difficult. I think one of the questions was also like, why do planes not come in the winter? And the reason is that it's so cold that the hydraulic fluid in the control surfaces freeze, so you can't, the ailerons and the elevators actually can't move. So getting a plane in here is almost impossible in midwinter. So this is why we also have to go through a fairly extensive medical screening before we come down here, just to make sure that we have nothing that might sort of crop up, in the middle of July. But yeah, I think almost anything that would come up here we could deal with.
That is great. Great to know. Glad you guys are safe down there. We have a couple questions about your daily schedule. How is your daily routine decided? Do you have a strict routine? And kind of related to that, how much maintenance does IceCube require?
So so we winterovers. So we IceCube winterovers. So our job is to keep the detector running. Luckily, the detector runs really smoothly, and we have uptime of 99.9%. And so it's very rarely that we have that things actually break. From time to time it happens, but it's quite rarely. And so we don't have a real schedule, so to say. I'm always saying I'm always working and never working. And because we are actually, so I'm saying I'm always working because we are always on call. So we have kind of radios, like those things. So when the detector breaks, when there's some issue with the detector, then the detector actually calls us, and then we respond, and we fix the detector then. But yeah, it's mostly we get something like something once a week or so, one of those calls. But yeah, our daily routine is basically, yeah, I mean, we try to have kind of a regular sleep schedule, of course. But usually our sleep schedule kind of follows the satellite times, because the satellite, actually the internet kind of changes by 4 minutes every day, and so our sleep schedule is kind of also changing a little bit from time to time. So currently I'm on nights, basically, what people call here nights. So I get up like at 2 in the morning, and then do some workout, and then in the morning, like at 5, the internet comes up, and we do like outreach events, or we just browse the internet. And yeah, and then in the morning, yeah, we have then breakfast, and then we do like IceCube stuff in case we have to do something. Every month we have to do like the calibration of the detector. That's what we do then, and so yeah.
Yeah, I'm doing a kind of biphasic thing. I'm sleeping from 1 till 5:30 twice a day, which works quite well. That kind of gets the internet and social stuff in the evening. So I have like a 12-hour cycle almost, which is, yeah, seems to work. I have like a work day and a fun day. As Martin says, we have a mixture of kind of scheduled stuff, and I'm currently on call this week, so it's it's not unusual to be paged in the middle of the night and have to go and fix something, but it doesn't happen too often.
That's what you all did as graduate students. But how do you stop snacking?
Yeah, it's very similar to grad school.
but how do you stop yourself from snacking all the time? And you guys look in very good shape.
So that's difficult. As I said, we have a really good baker here, and there's always cookies and things available.
Yeah.
So every time you go through the galley, it's very difficult not to just grab stuff.
Maybe your metabolic rate is high at the pole, so burn it off.
Yeah, I mean, we work into the gym every day.
I go to the gym every day, and go running and doing some weightlifting.
Good.
Well, that might be somewhat related to one of the questions about whether you've noticed any biological change in your bodies after long stays at the station. So you've been there for quite a few months now. Other than maybe going to the gym, is there something about being isolated there, or maybe not?
Well, I mean, maybe only because now it's kind of dark all the time. Well, during the summer it's always light, always bright all the time. So it mixes. The sleep schedule kind of changes a bit, and so it affects the mood a little bit. But in general, it's not too bad. And
I think it's fine. The first few weeks are difficult just because your body's frantically trying to produce more hemoglobin and whatever to increase your oxygen efficiency. But now it's fine, and the station's okay. I mean, we're kept very busy. I think I'm sure someone will ask this, is that we have a board and what kind of social things we do. And there's stuff organized basically every day in terms of social activity. So it's very difficult to get bored here. Almost there's not really enough time we don't have any free time. There's always things you want to do.
Yeah, that's great. And is everyone at the pole working on IceCube? Well, they're not all working on IceCube, but can you talk a little bit about the other people at the South Pole? What other experiments are there? Where are they located at the South Pole in relation to you?
So as I said from the first slide, there are 3 kind of really big like telescopes here. So we have IceCube, and there are 2 of us. There's South Pole telescope, and there's 2 winterovers for that. There's BICEP 3 and BICEP Array, and there's 1 winterover for each of those. We have Aurora cameras on the roof, so there are cameras that take pictures of the sky all the time. We have some radio arrays for auroras called SuperDARN. There is a seismological station somewhere, I think it's like 5 kilometers away, which is measuring a mixture of earthquakes. It also does, it's part of the Nuclear Test Ban Treaty. What else? We have ARROW, so the Atmospheric Research Observatory. That's probably one of the most important sites here because it's measuring stuff that is relevant to all of us, which is climate change. and they are one of the 3 sites around the world which that measure CO2 concentration in the atmosphere. So that's quite cool to have that here. They also do the ozone monitoring that I've mentioned before. What else do we do? Lots of, there are quite a lot of small experiments that are either automated or so we have 2 research assistants, RAs, who kind of manage all the random experiments on the station. So scientists make up around 1/4 of the population.
Oh yeah, and then of course you have also all the other people who are then basically maintaining the station. So we have plumbers, electricians, then of course the medical team, then chefs to cook our meals, and then UTs who are just making sure that the station is working, that all the equipment of the station is working, and then of course people who are running the power plant to keep our lights on. Satellite people, so what they call the satellite and
SATCOM engineers, IT. So the remaining kind of 30 people are keeping the scientists alive. That's the way we joke about it.
Yeah.
All right. Well, we have about 1 more minute until we have to log off, I think. So let's close out with this nice question. What do you feel is the best part about your job, Josh and Martin?
Well, the best part of our job is basically to, first of all, to keep the detector, keep IceCube running, take lots of data, lots of neutrino data. And then, of course, being here at South Pole at this very exciting and special place, where we see all the auroras during the winter time, these great aurora displays, and yeah, being together with really nice people down here and spending some great social time, basically.
Yeah, I think for me it's definitely the community aspect is great. We have a very close-knit community of people. It's fun to participate in all the weird traditions that we have down here, and yeah, it's a very special place to live.
Yeah.
Well, wonderful. I think that's the end of our time with Josh and Martin. We're going to pass it off, I think, back to Daniela.
Okay, I think that this was really an exciting, exciting experience. So you really took us almost there to the South Pole, and really brought back into us what it means to be a scientist, which means also to be an explorer, really looking for new things in nature and to understand nature around us. So I would like to thank everybody that has made this possible, including, all of our support here in Oxford, but also, Subir, Jim, Gwen, Martin, and Josh, and of course, Madeleine. I mean, you have made this experience truly, truly amazing. So, we are not in person here. We are all scattered really around the world, from Oxford to France to the US to the South Pole. But I would like to give you, the most heartfelt thank you and a big clap.
Thank you.
For everybody in the audience. Thank you again.
Thanks.
Thanks for inviting us.
Thank you very much.
Thanks. Have a great day, Josh and Martin.
Okay.
So yeah, still answering questions.
Oh, you're still answering questions. Okay.
Yeah, and I'll just add, thanks so much. We also had Lindsay, who did all the work on the logistics side for IceCube, and so in the background, and Val just did a wonderful job keeping us organized, and so it was a great team to work with. We wish we could have traveled to Oxford.
That would have been great.
Yes,
good old time. Yes, we would have
Yes.
liked to host you here.
Yeah.
It is a beautiful city, and today is a beautiful day here in Oxford.
Very good. Yes.
Okay, bye-bye, everybody.
Bye.
And thank you again. Bye.